Welcome to week 2 of your chemistry course. This week we'll be exploring chapters 15 and 16, where we'll cover acids, bases, and aqueous ionic equilibrium. Acids and bases. Now, most of us are, or at some point, have experienced heartburn, which is as a result of the acid in our stomach coming into contact with the lining of our esophagus. And when it comes into contact with that lining, it causes irritation. And this irritation is what we call heartburn. We may also be familiar with all the methods or the antacids that are used to treat this condition, such as Maalox, Pepto-Bismol, and there are quite a few out there. And their role is to neutralize the acids in your stomach. From an environmental standpoint, we're also familiar with acid rain, which occurs when we burn fossil fuels and liberate the oxides of sulfur and nitrogen into the air, and that combines with oxygen and water to form nitric acid and sulfuric acid. And that causes us to have a negative impact actually on our environment. Plants and even some of our man made materials may dissolve due to acid rain. So, we will be examining the impact of acid and base behavior on on our environment, on our bodies, because they are very important in the chemistry or the biochemistry of our bodies in our day to day life. Now, let's talk briefly about acids. In your lab, you will be familiar with sulfuric acid, or you have heard the term nitric acid. Those are some of the common strong acids that you would find in the laboratory environment. Or even in your regular day to day environment, you will come across citric acid in your limes or your oranges, or you'll come across malic acid in your grapes and your other fruits that you eat. Now, acids have certain characteristics that we use to identify them. They are sour in taste, and they tend to react with active metals. And by active metals, we mean aluminum, zinc, and iron. They're slow to react with, say, copper, silver, or gold, and they're also very corrosive. They will react with or carbonates to form carbon dioxide. So you'll see acids reacting with baking soda, limestone, marble, or chalk. And they change the color of vegetable dyes. And you've heard the term that it turns litmus. It will turn blue litmus red, and that is one of the main ways in which you identify whether a compound is acidic or basic, is by how it changes the color of blue litmus. And of course, acids will react with bases to form salts. Now, bases, on the other hand, you probably as well in your lab have heard of sodium hydroxide. Those are pellets of sodium hydroxide or calcium hydroxide. And you find a lot of these in a lot of our day to day cleaning supplies or everyday supplies, Lysol, Maalox, I mean, bathroom cleaners. You'll find a lot of these bases in there. And of course, the one you probably would be most familiar in your day to day environment would be baking soda. Now, some of the characteristics of bases. We also call them an alkali or alkalis. They have a bitter taste, but please do not go about tasting bases because they they might not be so good for you because they're often poisonous. A solution of base tends to feel slippery, and they change the color of vegetable dyes. Now, when they change the color of vegetable dyes, they do it a different color than the acids. bases will change red litmus to blue. It won't have any reaction with blue litmus. So bases change red litmus blue, and of course, they will react with acids to form ionic salts. And then we call that neutralization. Now, over the years, there have been many definitions of what an acid is. And there are three main definitions that we use or that we refer to. There is Arrhenius definition, the Bronsted-Lowry definition, and the Lewis definition. Now, the truth about it is no single definition is per se correct. Rather, each definition is useful in a particular instance. And so we're going to briefly discuss these types or these definitions of what an acid is. So, one of the first definitions was by a Swedish chemist called Svante Arrhenius, and we call this the Arrhenius definition. And his definition basically states that acids produce H plus ions when they are in solution, whereas bases will produce OH minus ions in solution. And note the important thing is this is in a solution. And this is one of the first definitions of an acid, and this was in the 1800s. So, according to Arrhenius's definition, when HCl or hydrochloric acid is in solution, it will dissociate into H plus ions and Cl minus ions. And this is when it is in water. Now, sodium hydroxide, on the other hand, will dissociate to form Na plus and OH minus ions. And so in this case, NaOH is a base because it forms OH minus ions, whereas HCl is an acid because it forms the H plus ions. And note, both of these take place in solution, and that's why we have that AQ sign at the bottom of each of these compounds, is to denote that they are in aqueous solutions. Now, for HCl, if you recall, hydrogen group 1, chlorine group 7, HCl is actually a covalently bonded compound, and it doesn't really produce H plus, but well, it does, but as it produces H plus, it's highly reactive, and so you never find H plus ions sitting in solution. It always exists as what we call the hydronium ion, which is a complex of H plus a molecule of water. And you will come across this in chemistry a lot, where we describe the hydrogen ion or as the hydronium ion or H3O plus. With sodium hydroxide, this does not matter because it is an ionic compound which will dissolve into forming OH minus ions. And this just shows the structure of the H plus ions and combining with water to form the hydronium ion. Now, the second, and it's probably the most widely applicable definition of acids and bases, is called the Bronsted-Lowry definition. And it was introduced in 1923 by Johannes and that's Bronsted and Thomas Lowry. And basically, what they describe an acid as, they describe acids as proton donors or H plus ion donors, and bases as H plus ion acceptors. So, according to this definition, when HCl is in solution or any acid in solution, the the H plus ions um, will, or the HCl will donate a proton to water, and that would form the H hydronium ion, H3O plus, and it also means that the bases, the proton acceptor will accept the proton in solution. Now, one of the important thing is Bronsted-Lowry bases tend to have a lone pair, and if you remember from your earlier work, a lone pair is really a non-bonded pair of electron. In this case, you're seeing NH3 from ammonia with its lone pair and the two lone pairs that are in the water molecule. So in this case, NH3, when it reacts with water, the the base is the NH3, and water then acts as the acid because water will donate the H plus ions to ammonia and it forms the OH minus. Now, Lewis acids and Lewis bases. Now, the Lewis definition of acids and bases was described by an American called G.N. Lewis. And what he focused on is that while the Bronsted model focused on transfer of proton, Lewis focused on transfer of electron pairs. And so he describes an acid as an electron pair acceptor and a base as a electron pair donor. So here we have a typical Lewis acid base reaction where we see oxygen, the compound containing the oxygen here, acting as the Lewis base by donating its lone pair of electron towards the carbon, and then the carbonyl compound accepting that electron, and so it is the Lewis acid. And when they combine, they form an adduct. And here again, the same compound is trying to is acting as a Lewis base again in the reaction with HCl, which now acts as a Lewis acid because it's accepting that non-bonded pair of electron. And probably one of the most popular Lewis bases is ammonia with its lone pair of electron, and it donates that lone pair to boron trifluoride in its Lewis acid reactions to form the ammonium boron trifluoride adduct. So that's a brief overview on acids and bases, or definitions of acids and bases. Hopefully, it will be a lot clearer to you all. Thank you very much.